Hello, everyone. Welcome to the second episode of our series. Today, I want to talk about the sensor data normalization, which is a natural second step after you get data to your data platform that we have discussed last time. Now, feel free to check our GitHub repo where we have a code for episode 1 here. And after this second episode, we're gonna add to the branch episode 2 the code we're gonna build together today. So going back, for those of you who maybe missed the previous one, let me quickly introduce myself. I'm Thomas Neubauer, CTO and co-founder of Quix. And I have spent my whole career working with sensor data, mostly from some big machines that I use for development. So whether that is a simulators, wind tunnels in F1, heat chambers, or test benches when you run devices to test them. I also worked on F1 cars to get the sensor data from them, and on first response vehicles and coordination of those vehicles in critical situations. So that's me. And today I want to really immediately jump to a whiteboarding session to walk you through what to do with data coming from machine. Because there is a journey between I'm getting data from something like MQTT or PCUA or HTTP gateway, and I have a data in a database which I can comfortably leverage to analysis, but also a data which I can use to make insights into data, whether that's batch or real-time stream processing insights, doesn't really matter really. So I'm gonna stop sharing here and share my tablet, and let's go through the whole process and all the pitfalls of data normalization together. So I will join the meeting from my tablet, and we can give it a second. Good. So hopefully you're gonna see now my my screen, my tablet. There we are. And so let's go to whiteboarding session and let's create a completely brand new canvas. So as we discussed last time, so let's quickly just remind ourselves what a, let's say, good architecture might look like. We have discussed the bad architectures last time, but let's discuss the good one and what is the next step if you get that right. So you have some sort of machine, and whatever that is, that could be the simulator, that could be the wind tunnel, that could be a test chamber, whatever. And usually you will have some sort of agent running on the local machine, whether that's PC or some laptop here, which will use either some proprietary interface of this machine, when that is the case, or it could be OPC UA, it could be LabVIEW running on the agent here. That's not important for today. But that will probably send something to, let's say, MQTT broker. Let's be a bit optimistic here. We have that. So we have MQTT broker. And then that would be the last step when it's reached the data platform. So here we're going to have the MQTT source of our stream processing pipeline. So if we kind of create, this is on-premise, and then we're gonna have the cloud or just data platform infrastructure. So what the data looks like here? Well, when we use MQTT, that's quite familiar format. So you're gonna have a topic tree, and MQTT really relies on that. So you might have something like a room one. Inside you have a machine A, and inside that you have maybe temperature, and even inside, and the same level humidity maybe. And it's a topic structure. You can subscribe with MQTT just for machine A, for example, or even for just a temperature. That's a nice thing about MQTT. And that is a topic. And then you have a payload. Now, sometimes what we see is that you get here directly a number. So you can have here a temperature of 21 degrees, and here maybe a 50 as a humidity. Sometimes we see a payload instead. So for example, you might have a JSON where you have a property value, which is 21, and then maybe a timestamp, which is some Linux epoch there. Why you might see this? Well, because actually a timestamp of data entering the broker versus a timestamp of data being captured could be different. And not taking attention to that could lead to a discrepancies in your data, especially when you do the pre-processing that we're going to do today. So the way how it happens here varies, but there would be a moment where the sensitive value is actually captured, and that might be significantly earlier than the data lands into MQTT broker. So it is quite important. And then if we look at this structure, and this is really important mind operation, and we have to do today a lot, is to look at the data like a tables, because it really helps to understand what we're doing with them and all the operations. So if we look at data like this, so you have a MQTT broker, what we're basically seeing is that we're getting data that looks like something like this. And if we take this data and we directly store them in Influx, Timescale, QuestDB, or just Postgre relational database, the result table would look like this. You're going to have a timestamp. Then you're going to have temperature. No, I'm too fast. Sensor ID. And then you're going to get value. And what you're going to see here is probably 10, 0, 0, 0, 0, temperature, and 20. And then you're going to get 10, 0, 0, 0, 1, humidity, 50. And it's going to go, you're going to get temperature again, 25, etc. Maybe here, humidity, 55. Okay. Now, there's nothing wrong about this format, and you can persist it. Actually, you should persist it because although it might be a bit more difficult for analysis later, it's also more robust in terms of any problems like out of order data, missing data, some sensors being more delayed than the others, etc. So this format has its advantages, but one of the disadvantages why we're gonna have to do something with it is that in order to cross-reference the parameters, you getting into quite difficult operations. So it doesn't matter really if you're doing a SQL query to a database or you're doing stream processing service that do something. But the moment you do something that where, for example, a condition to have to do something is where a temperature is above 20 and the humidity is above 50, you see here that's a bit difficult because each row have a different sensor value. So you can't write a SQL query easily like that. Equally, where each row represents one message in Kafka topic, you're going to have a stateful operation that's joining these things together. Now, this is where you get to the problem of not just where you do it from sort of architecture point of view, but you're getting into where to do it for skill who is need this and who can do it, because a software engineer or data engineer maybe can perform a stateful stream processing operation like that, but if you delay that to somebody who actually understands the data being sent, some mechanical engineer who's actually doing some meaningful analysis of the data, for him or her, that might be too difficult because it's a computer science issue, problem to solve. So this is why we might want to do this before we land the data to the database, or we might want to create a secondary table in the database to have this nice structure where we can do these queries. Equally, if you're, for example, calculating some function, so let's imagine you, for example, want to calculate a lead bulb value here, which consists of the temperature and humidity, of course. Well, you can say, well, okay, temperature multiplied by, I don't know, humidity divided by 2. Of course, the actual formula is much more complex, but you can't do that. Again, you need first to normalize the data. So what we really gonna do here is we're gonna first transform this table from rows to columns. So we're gonna make a transposition where first we're just gonna make the rows columns. So you're still gonna have a time, but you're gonna get here a temperature and humidity. Okay, and then if we go back to the timing, then it will be something like that. Okay, now that's still not ideal because, of course, we have gaps in our data. This is not ideal for a storage, whatever you use, but it's also not ideal for the queries and functions because you're gonna have to deal with a lots of nones, nulls, depends on the technology you use. So at this point, what you want to do is to produce something which is gonna look like this. Sorry. So you're gonna start again at 0, 0. But we're gonna use here like that. Now, this could also be, and this is just a, how you agree with inside the company. This could also be something like that. Well, you might be asking, what I'm looking right now? Well, basically, this row is now this period of time. Okay? And this row is actually this period of time. And then this value is a representation of aggregation of this area. Now, you can do this downsampling to what rate you want. So this rate is the minimum rate to get the source rate. But you can do it a factor of 10. So you can have, every second you can have some numbers, a number from a sensor, and then you can have one row per 10 seconds. So that means that each value represents 10 values in an incoming source. And then, of course, the type of aggregation that you use here matters more than now. But anyway, this is where we're getting to a much nicer table, which will be quite compact. It will allow us to create data with simple SQL queries. Everybody can do that. And if you build some stream processing service that will consume this data, again, your life can be very simple. And your service can be stateless as well. Because now you can process row by row, message by message, and you don't care about the previous row that much. So now you can, for example, say, okay, well, I'm going to create here a function. And the function, and this is a product of that number and that number, okay? And your life is not much simpler and easier. Now, of course, this is without its pitfalls. So this approach gonna have some issues. If your data source is unreliable, unordered, or produce data at vastly different frequencies. So if, for example, the temperature comes 5 seconds behind the humidity, just maybe because the circuit that controls that sensor is just different than the temperature humidity has a different part of the systems in the machine, you're gonna have to wait for the data to put it back to the cells. So that's one thing to look after. All right, so now this is the theory. Now let's go to our data platform that we have used, the Quix platform that we used in the previous episode, and let's basically code this service. And we're gonna call it data normalization. This is usually a service that you put before your dbSing. That's gonna write the data to the database of your choice. Okay, so let's do that. So I'm gonna stop sharing here. Cool. And let's go back here. So we're gonna share my browser again. Hopefully you can see it. And let's go to our pipeline. So this is what we have created last time, if you remember. This is MQTT source, and it's giving us this data. So fan speed, nozzle temperature, print speed, etc. from a 3D printer. And here we have the values. Lovely. Now, we're gonna go into a scratchpad of episode 2 of this webinar, and we're gonna create a new service here called, my keyboard fall asleep. Yeah, data normalization. Good. So the one thing to understand is that MQTT gonna have a different system for the messages, especially around keys. So we're gonna have to take that into account. We're gonna have to convert the two systems into between each other. Now, this is where we're also abstracting our downstream systems from the way how we get data in, because today is an MQTT, tomorrow it could be something else. And it's important that we don't drag the dependency on that technology into everything we build. So let's comment out the output until we have something to publish. And let's create an output of this service called sensor table. Sensor data. Good. So let's just run this service and let's identify it as a data normalization v1. And let's get the data. Cool. So now we see that each message, which you can see here like that, has a key, which consists of a name of the machine, the name of the sensor. Then we have a value, which is just, just a number and a timestamp. So the first thing we're going to have to do is understand that our key is string. This is what our MQTT source is doing, converting the topic structure into message key in Kafka. This is where we move from one word to another. Because Kafka does not have the topic tree architecture. It just has a flat topics, and they are used differently. You use message keys to separate data into streams, and you use much richer message payloads than using MQTT to send your data. So the first thing we're gonna do here is actually do exactly that. So we're gonna take the actual messages and we're gonna have a value, key, timestamp, and headers which we're not gonna need. And we're gonna here create a message payload where the first is a timestamp. That's simple. We don't have to do anything about that. But then we have the machine where we already see that key is split by that. And then we're going to have a sensor ID. Remember our whiteboard? I'm just copying exactly that situation. This is a bit up. This could be done better, but for simplification today, let's do that. And then we have the value where, again, we just take it as it is. Now, let's run this. And instead of this, let's use the print table visualization, which is a bit nicer for this type of data. So here, we're doing exactly that mental shift where each row is one message. That's to really visualize the data in the topic. I have forget to tell that I want message key and message timestamp in my overload. All right, so now you see that's looking better. We have some data. The timestamp is there. So I'm not sure why it's disappeared now. Let me run it again so it stays there. Some rendering glitch of the console. Good. So now what you can see here, that this is a key of the message. This is the timestamp of the message and the timestamp we have produced in our payload. So this is coming from the value of the message. This is coming from the metadata of the message, the first two columns with underscore at the beginning. This is same. So that is good, and we don't have to do anything else. If we would have the second case we discussed in the whiteboard, where the timestamp actually coming from the JSON payload, we would have to do an operation called set timestamp. But we don't have to do it today. But we have still this structure, so it's a bit difficult to, to do the cross-parameter referencing that we discussed. So let's do another apply where we do row to column normalization. So at this point, we have row, not value. And here we gonna start with timestamp, which is gonna be the same. So we're just copying that over. And machine also is the same. But then we're gonna do the sensor ID as a name of the column, and the value is value. And let's disable the metadata columns so we have a bit more space to print. So this is going to be quite interesting. All right, so what you're looking at right now is as the sensors coming in, the columns are appearing and they are just zigzag appearing. Well, that's because that's how the, in our case, OPC UA source, which is before the MQTT bridge, is producing the data. Now, that's almost there, but still, if we now, freeze the motion, we have a fan speed, but we don't have a print speed, and we don't remember what was the last one. So that's quite difficult, isn't it? Now, this is where we're gonna have to build a stateful operation, which will normalize the data here for something nicer. So let's first, before we actually do that, let's get our timestamp to a bit easier to read. So we can get the so we have here a epoch. So I'm gonna import a data time and convert this epoch in milliseconds to a string that we can read as humans. Now remember, this expects a second precision. And just for space, let's just get a timestamp here. Or maybe not, I think this is good. Let's just run for now. Nice. So what you see here, and remember this print is artificially slowing down the data so you can see it as a human. But you see that there is a lots of messages even per second. So that's going to be quite interesting. So what we're going to do now is here create a tumbling window. And here we have to decide at what frequency we want to output the data. Now, if we set the tumbling window of 1000 milliseconds, that's basically at 1 Hertz output. We can change that, and we will do later, to play with that. There are different ways how you can do this normalization, where you don't drive the timestamps, but you let the input data drive timestamp. But I don't recommend that unless there is a real value in exact, millisecond where the sensor was captured. Because if you drive the timestamps with a tumbling window, you're gonna have a nice rounded timestamps, and that is much easier to work with when you are plotting them or do any sort of aggregations later. So here we're gonna aggregate, and here we have to, for each column, specify what sort of aggregation we're gonna make. Now, here's the thing. You can do this dynamically or take care of each column by yourself. I'm gonna do the second today just to make it a bit easier to understand. But sometimes it's even better because it's a bit safer for schema involvement and validation, which we can discuss later. But first, let's import last, count, and mean. Good. So here, what we got? So we got fan speed, we get bed temperature, and we have print speed. There's one more, but I just want to keep it a bit leaner so it's easier to visualize for now. All right. Now, if I put here final and print it, and actually to make it a bit nicer here, all right, you see still a lot of gaps. And I intentionally made this mistake to explain a very important concept. So you might be asking, well, why it doesn't work? I mean, this is all, they have all the same timestamps. Why my aggregation is not kicking? Why I don't have always the last value of that of the interval? Well, it's because message key. You see, Kafka use message keys to build streams. And we are here doing an aggregation per machine. But our message keys are per sensor. This is not going to work. We have to repartition our data. So this makes sense because this is representation of a machine, not a sensor. So what we have to do here is do SDF dot group by machine. Now, you know, if you would have different structure, you always have to decide what is your stream, which columns belongs to each other, which rows belongs to each other in your stateful operation. Now, if I do this will change. Oh la la. So now our table is compact, filled with the data. It's because we're doing the last. Now you might be asking what these values actually represent. Well, they represent a bucket of data worth 1 second between start and end. So you see, every second we have one row. That's because we have set our tumbling window to be 1000 milliseconds long. Now, if I change the last to count and run this, the number will actually represent how many values were in that bucket. And that's why if the number is very high, you might consider using mean instead, the count. So here you see, yeah, there are lots of values for each sensor per second. So at this point, you probably want to use mean here and take into account possible, variations coming inside the bucket that this value represents, or this is maybe the moment where you want to reduce this. But you have to be careful with reducing this number, because what happens if I put 10 hertz output? Let's do that. So now instead of 1 second, we're going to produce a timestamp every 100 milliseconds. In other words, we're going to produce 10 rows per second. But at that point, we're getting into a danger, you see? Because not always we're getting at least one sensor readout per the period. So at this point, we have to change the way how we do this. We have to go and change this from a tumbling window to a hopping window. And hopping window has a useful feature where the window is not going every second or every 100 millisecond moving to the right, but it's a 1 second window moving 100 millisecond every 100 millis. So it's like it's moving to the right. That will give us always at least a 1 second worth of data, and we can pick the right value from it. So if you use last, we're gonna drag the last value for the periods where we don't have the numbers. If we use mean, it will be sort of rolling mean, So now if I do here a last, which I think makes more sense, this sort of operation. We're gonna get this time amazing structure. All right, now you see we still get some nuns, and that's because the second might not be enough, and you might want to increase this to 2 seconds maybe. You might also find out that you're getting nuns because some of the sensors are a bit delayed. And that is where there is another graceful period where you say, okay, regardless of the timestamps, I want to wait up to this amount of time to a delayed arrivals. So they don't get, so their train will not leave the station without them. Because you can imagine that each window is a train waiting in a station, and passengers are going to the train, and then when a next time window arrived, the train will leave the station. And here we're saying how long the train will stay in the station for late passengers to hop in. Now, the last thing I want to discuss is a schema evolution. So what you might get is a system which is not reliable in schema. So based on the configuration of the machine on input, some sensors might not be emitted. Now that could cause a problem for your storage, for your queries, for your dashboards, for anything. That's why you might want to introduce a schema which will not be always fully filled, but will be captured and saved in database. So let's imagine that we know that at some cases, there's more than those three. Then what we want to do here is say, okay, so we're gonna get a fan speed, we're gonna get the bed temperature, we're gonna get the print speed, and we're gonna get, I don't know, aux temperature, okay? Now in this case, we know that this sensor is not being collected, but tomorrow it might. And we want to keep this schema static. And that's why we're going to do this. It is very practical thing to do. So now we're getting nuns, and that's fine. And, they might not be nuns forever. The last thing you can, of course, now do is to calculate something. So you can, of course, here, probably in different service, but I'm just going to show you it here. You can create a function which is, I don't know, a fun speed multiplied by, I don't know, bed temperature. And because we have this amazing structure now, this will actually work. And that's the whole purpose of our data normalization. So the last thing we want to do here, yeah, it's working. So let's remove this and let's uncomment the topic bit. Let's change this to sensor data topic. I think that's sensor configure. This is going to be silver topic because it's already the data already procured, and we're going to deploy this. But because it's a stateful service, we have to give it a state. Cool. And if we wait a second when this is deployed, you will see how the output is going to look like. So this is the incoming data, which we already reviewed. And here we're going to get the data in a second. So now the key is machine, and the payload is our lovely format. What you probably want is to rename the start to timestamp and maybe drop the end, or other way around, keep the end as a timestamp and drop the start. But sometimes you want to have that information. It depends on your normalization. But now you are ready to, well, sync it to the database, but also consume it in stream processing projects. So hopefully it helped, guys. And you can, after this webinar, check the GitHub repo. Here, I would create a PR into episode 2 branch with this code that we have created together. And hopefully, if you want, you can just use this repo, fork it, and import it in a Quix platform. And it will work with single click of a button, exactly how it worked for me. So yeah,